So, in the previous lecture I talked about Schrödinger equation, which is the equation for an electron in hydrogen atom, which is supposed to give all the informations about energies and all other things, and the equation was minus h cross square over 2m, then this del square of psi plus potential energy function ur psi is equal to E psi. E is the energy, and this psi, which is a function of a space point, this is called wave function. And I would like to tell more about what this wave function is. First of all, we are talking of electron, supposedly a particle having a proper mass, a proper position, a linear momentum, and so on. But for that electron also we have to find this wave function. As was the case with light, which sometimes displays wave property, sometimes displays particle properties. You saw that diffraction experiment. In certain directions the probability of light going is 0, in certain directions it is very high, and in other directions it is somewhere in between. So that is like a wave. And then you have other things, photoelectric effect and other things, where you have to think this in terms of photons. Similarly for electrons also. Electrons also have wave character and particle character. The wave character is used in varieties of electron microscopes and other things. Electrons can be diffracted and can give you those diffraction kind of structure, where in certain directions they go with larger intensity, in certain directions they do not go with larger intensity, or they do not go altogether 0 intensity. At the same time, electrons are particles. When we detect electron, we detect one full electron. So electrons also have this dual character, and therefore together with energy and momentum, we also have to talk about that wave function, wave character. So that wave character is described in terms of this wave function, and not only the wave character, this wave function itself will describe the particle character also. Okay. So this wave function psi, which is a function of a space point, if you write this, what is called mod psi square. What is that mod? This function, this can be a complex function. Can be. If it is complex function involving the square root of minus 1, remember complex numbers, the numbers like some real number plus this is written as I, so IA plus IB, these kind of things, real number here, and then this is square root of minus 1 here. These kind of numbers are known as complex numbers. So this function can have this I in that, and then you write the complex conjugate A minus IB. This is called complex conjugate. So if this thing is Z, this thing is written as Z star, and if you write that Z star into Z, that will be A square plus B square, and this is known as mod Z square. This is also known as mod Z square. So it is essentially the same thing. If you have this psi, it could be complex, take complex conjugate, multiply by it, and then take this this whole thing, this is mod square of psi rs. Okay. So if you have this quantity, then you can connect it to something which is physical, and that is, suppose here is that proton sitting at the origin and the electron can be somewhere, and you want to know that at this position r, let's say this is position vector r. So here I construct a small volume, and that small volume is, let us say, d tau. So you have a small volume d tau at this point, constructed at this point, and that point has position vector r. So there is some value of this wave function here, that is the psi r, and make this mod psi r square multiplied by this d tau. This gives me probability of finding the electron in this d tau. Okay, so this psi square, mod psi square d tau, this quantity gives me the probability of finding the electron here in this volume. So if you want to know where the electron is, if I put some instruments to locate it, where do I locate? So you can locate it anywhere in this space, but with different probabilities. If at a certain point you do not have this wave function, finite value of wave function, suppose this is 0 at certain point, then there you said, okay, electron will not be found. But if this quantity is large at certain position, then you say that, okay, in that vicinity I have larger probability of finding the electron. So that's the meaning of this wave function. Okay. Now this wave function psi, this is a continuous function of xyz, right? It's a function and it's a continuous function. But then there are certain conditions on that. General conditions, not only for hydrogen atom, general conditions. And the first condition is, since it is representing some kind of probability, if the force is coming from from a finite region, the probability of finding that particle at infinity should be 0. If that force is confining the particle, then at infinity should be 0. So if I say that we have some axis and the force is coming from here, and then I write psi and this psi r, and the condition should be that as r tends to infinity, what is this r? This r and this r is related. This is the position vector r and this is the distance from the origin. Okay. So if as r tends to infinity, this psi should go to 0. So that is one, it should go to 0. You cannot have a finite probability of finding in the whole of the universe till infinity. Similarly, if I go for this psi r mod square d tau and integrate over all space, this gives me the total probability of finding the particle somewhere in the whole space. That must be 1. If it is not 1 but some finite quantity, I will just multiply my wave function by some constant. That doesn't change the character, the functional form remains the same. So if I put that constant here, I can always make it 1. But if this goes to infinity, then I cannot do that. So we say that this wave function should be square integrable. This is known as square integrable. That means if you do mod square and integrate, you get a finite quantity. If that finite quantity is 1, it is fine. Otherwise, we will just scale it. We will put some constant here and make it 1. But it should have finite value. It should not be infinity. So these are some of the things. Of course, psi must be continuous. So these are some conditions that this wave function has to follow. Continuous. But so these are some of the conditions that this wave function must follow, and it turns out that if you put any arbitrary values of this energy capital E, in general you may not get any functional form psi which satisfies the equation with these boundary conditions, right. Your equation is here. So suppose it is hydrogen atom, I am talking of hydrogen atom, and what do I mean here? When I am talking of electron in a hydrogen atom, that is here. That means this UR that I am writing is minus E square over 4 pi epsilon naught R. Once I write UR is equal to minus E square by 4 pi epsilon naught R, I am talking of hydrogen atom. If I am talking of something else, then this UR will be different. So suppose this is the equation, and suppose for this E, this capital E, suppose I write 1 electron volt, and okay, the equation is still there, and I ask that tell me what is the psi, what functional form psi I should put here, so that when I do all that second differentiation with respect to x, y, z, etc. Remember that this del square is del 2 del x square plus del 2 del y square and plus del 2 del z square. So if I do all those operations on this psi and write this equation, where are the what values, what functional forms of psi I can have? And the answer is that you cannot have any psi. You cannot have any psi if this E is 1 electron volt or 2 electron volt or 1.5 electron volt. So only for some specific energies, only for some specific values of E, you can find psi. So that's the first thing. And in this particular case, it turns out that those energies are given by minus ME4 divided by 2 into 4 pi epsilon naught square h cross square and 1 by n square here, where n is equal to 1, 2, 3 and so on, some positive integer. Only for these values of energy, you can write it En, only for these values of energy there are some functional forms psi, and if you put anything else, then you do not have functional forms psi which satisfy the equation as well as these conditions on psi. So these are the allowed energy states according to the Schrödinger equation. And you remember, this is the same expression that we got from Bohr's circular orbit assumptions, and L is equal to NH cross the assumptions. So the Bohr's model gave me the same expression, and that is why the agreement was so good. Okay, the next question is, fine, let us put one of these energies here, and then what is psi? And I will give you the answers. Okay, I will not solve it, I will give you the answers. So let us start with n is equal to 1. That means the energy is minus 13.6 eV. So we put this energy here, what are the values of psi? And turns out that you have a psi which I will write 100. I will just tell why it is 100. It is not 100, it is read as 100, and that is square root of 1 over pi a naught cube e power minus r by a. This a naught is same as that Bohr radius. A naught is that Bohr radius, which is 0.053 nanometers. And r is the distance from the proton, distance of electron from proton, and this a naught is same as this a naught, the Bohr radius. So this is the function. This psi you have to put here, and this energy you have to put here, and the equation is satisfied. Now these three digits that I have written here, they are in fact three parameters in terms of which these wave function are described. I will tell what those parameters are, but let us first go for n is equal to 2. For n is equal to 2, E will be this divided by 4, so it is minus 3.4 eV. Anything between these two, if you put here, you do not get any solution, you do not get any functional form of psi. So the next energy available or allowed is this. And if this is the energy, then what is this psi? And it turns out that it's more than one functional forms which are possible. In fact, 4 of them are possible. And what are those 4s? There are some expressions which I will not write here, but there are 4 which we write 2. This is 2. We write 2, 0, 0. Then we write 2, 1, minus 1. Then we write 2, 1, 0. And we write 2. And then here 1 and here 1. So you have 4 different functional forms. There are 4 different functional forms, and with the same energy minus 3.4 eV here, they are solutions of this equations. So we have 4 allowed different independent of each other functional forms, all corresponding to the same energy minus 3.4 eV. And similarly, if you go for other energies n equal to 3, n equal to 4, those number of independent wave functions will keep on increasing. So what we write is this as psi n, L and ml. So these wave functions, the allowed wave functions which correspond to fixed energy, they can be written in terms of these 3 parameters n, L and ml. So the first digit here is n. This is n. N is equal to 1, n is equal to 2, then you will have n is equal to 3 and so on. And the second parameter, this is L. This L can go from, so n can be 1, 2, 3 and so on. So here n is 1. This is the energy, this is n equal to 2, this is the energy, n equal to 3, the energy will be minus 1.5 eV and so on. So that is n. So this n is, you can say it is related to, at least in this case, it is related to energy, at least in this case. And then this L can take value 0 and onwards 1, 2 depending on, and it should end at n minus 1. So if n is equal to 1, then this n minus 1 is 0, so it should end here itself. So for n equal to 1, the only possible value of L is 0. So here n is equal to 1 and only possible value of L is 0. This L is related to, angular momentum, and in fact we call it orbital angular momentum. Okay, don't go by the meaning of orbital, it is there's some orbit or so, just take it as a name. Orbital angular momentum. In fact, it is related to the magnitude of orbital angular momentum, and this magnitude is square root of L plus 1 times h cross. So that's the magnitude of angular momentum. And then this ml, third one, this ml, that should go from minus L in steps of 1, so minus L plus 1 and so on, and should end at plus L. And this is related to z component of this orbital angular momentum. So physically you can relate this n, L, ml to these quantities, and the wave function is written, is a function, but that function will have somewhere this n or L or ml and so on. In this particular case, the function only depends on r. It only depends on r. So that's okay. But if you go for other these functions, then you have more dependence, more complicated dependence. So that is the kind of wave functions one has to write. Okay, so we wrote about orbital angular momentum, and I specified that that word has to be there because there is another kind of angular momentum which electron possesses, and that angular momentum is not related to any motion of the electron. That's the best part of it. If something goes in some path, you calculate angular momentum r cross p. So if there is some linear momentum and the position vector r cross p is the angular momentum, that's fine. If there is no motion, no p and no angular momentum. But then for electrons and also for protons and neutrons, a very, very interesting thing, which again is a characteristic of quantum physics only, there is nothing like that in classical physics, that each electron has an intrinsic angular momentum, a built-in angular momentum. Even if it is not moving, the angular momentum is there, and if it is moving, then that extra angular momentum because of the motion, that is this orbital angular momentum. So any kind of motion of electron gives rise to angular momentum, that is orbital. And then there is some built-in, whenever electron is created, it is created within angular momentum, and that is called spin angular momentum. And how do I know about it? I know about it from the magnetic moment. The angular momentum of a charged particle is related to the magnetic moment, and magnetic moment can be measured. So from there I know that each electron, each proton, each neutron had some angular momentum which is all built in there, not because of any kind of motion. Now for electron and also for proton and neutron, it turns out to be the same. This spin angular momentum has a magnitude which is s into s plus 1 square root of this times h cross. This is that magnitude. For orbital angular momentum, the magnitude is square root of L plus 1 h cross, and this L can take values. It can be 0 or it can be 1, it can be 2 and so on. It can have values depending on different conditions. In the same structure I am writing the magnitude of spin angular momentum, and that magnitude is written as s plus 1 into h cross, and this s has a fixed value. It is half for an electron. for any electron, all electrons, and in fact all protons also, all neutrons also, there are many fundamental particles, they will have a spin angular momentum of this magnitude. Other magnitudes are also possible. For electrons, no. Protons, electrons, neutrons, there is a fixed angular momentum magnitude. Okay, so we call them spin half particles. These are spin half particles. But if you measure the z component of a spin angular momentum, the z component of spin angular momentum, there are two possible values, and these two possible values, so I am talking of now Sz. So there are two possible values, and these two possible values are half h cross or minus half h cross. So these are the two possible values of Sz, that means possible values of z component of spin angular momentum. You can write this as ms h cross, where ms is minus half or plus half. Okay. So it's almost similar structure: orbital angular momentum, spin angular momentum. Orbital angular momentum is magnitude is given by this number L, which can take different integral values, but for spin angular momentum, this is given by S, and S has a fixed value 1 by 2. And then the magnitude has the same formation, mathematical formulation, square root of SS plus 1 into h cross, here square root of LL plus 1 into h cross. Z component is, okay, here the Z component of angular momentum, that also I could have written, that is Lz is equal to ml times h cross. Okay, the Z component of orbital angular momentum is ml times h cross, and that ml can take values minus L, minus L2 plus L in steps of 1. Similarly here, this Z component of spin angular momentum, that is ms into h cross, this is Sz. So Lz is ml into h cross, Sz is ms into h cross. And just like this, ml can take values from minus L to plus L in steps of 1, here this ms can take values from minus S to plus S in steps of 1. So that will be minus half to plus half in steps of 1, and that is minus half and plus half. So now you have 4 parameters. Now you have 4 parameters, N, L, ml, they are there, N is there, L is there, ml is there. If you give these 3 parameters, that space part, the behavior corresponding to space part x, y, z, that is fixed from here. And if you give this ms also, because S is anyway fixed, if you give ms also, then that spin part, behavior of that spin part, that is also fixed. So if I give all 4 of them, if I tell what is N, if I say what is L, if I say what is ml, and if I say what is ms. And all this is for fixed energy states, stationary states. So if I give these 4 parameters, the entire behavior of electron with that energy is can be obtained from here. So I will stop here today, and next lecture I will be talking of what is known as quantum states.